Yeah. Hey, it looks like it's time. Excuse me. Welcome back, everyone. So for today's class, we're pretty much just going to be working on section 13.3. Excuse me. And we're probably going to be finishing it either Monday or possibly Wednesday of next week. Also, this class is kind of special because we don't have any quiz that's due today nor tomorrow. Instead, we pushed the quiz 8 to this week. So the due date of this one is officially, oh, hang on. That was supposed to be pushed, and the due date was supposed to be pushed as well. The due date on that one is officially November 6th. Sorry about that. Yeah, so there's no quiz actually due today since we pushed the quiz that was up here down. Sorry, I need to move the due date as well to make that official. But also, we're not going to hold class tomorrow night due to Halloween. That's one of those weird class cancellations where when you do hold class on Halloween as a night class, you're supposed to, but no one ever shows up. So it seems just rude, like everyone's getting behind because we held that one class. So we'll cancel this one and be back on track next Monday. So it's kind of like an early weekend, at least for this class. But any questions at the moment, folks? Okay, we all get pretty into our routines and patterns. So I'll also put out just another reminder through the Moodle system. So check your email for those kinds of things. So it looks like we're in section 13.3, but not sure why I said but here we go. In section 13.3, it starts off with lots of information. It kind of feels overwhelming when you're staring at that all at once. But this is really just a rundown of everything we've been encountering all the way back since 13.1. In 13.1, we defined our new variable, p hat, or rather statistic is a better way to say it, as the number of successes in the sample divided by n, meaning we're dealing with categorical data with only two outcomes, something we'll call a success and something we'll call a failure. But then the central limit theorem comes into play. This is the most abstract part of the course right there. It says your statistic p hat, in fact, came from a normal distribution, approximately. And that approximation gets better and better as the sample size gets larger and larger. So now that we have the central limit theorem in play, we can now use probabilities involving p hat. The assumptions and conditions here we had looked at majorly in the last section. That was a major push for 13.2. But these are conditions upon which the central limit theorem is going to be considered effective. Then going beyond that, another big problem we have is that P is unknown in our problems. It's the population parameter. Our whole goal is to estimate it. And that means the standard deviation is unknown at the same time. And so what we do is we reach for the statistic. Just because this is unknown, it doesn't mean we can't just estimate it. And so down here, we make that estimate by putting p hat in place of p. With all these things in place, we're now ready to describe what the whole confidence interval is going to look like. Any questions at all, folks, running through this kind of synthesis of information? Okay, so here's where the new information starts. Putting that all into play, we have the large sample confidence interval for a population proportion P. It's got a long name. That's how you, I guess, can tell it's important, I suppose. The process says you have to gather a simple random sample of size n from a population with unknown population proportion of successes P. We usually highlight this in blue in the notes. To estimate P, we have to make sure we really do have a simple random sample. Second condition is that the sample is large enough so that there's at least 10 successes. So this part is the successes and at least 10 failures. So that portion there is the failures in the sample. Really, these two bullet points right here are just these two right here, the randomization and the success failure condition. We won't run through all three of these on every problem, mostly looking for randomization and the sample size being large enough. Okay, so we've got conditions, we know what we're estimating, and it goes on to say, when these conditions are met, a confidence interval for the population proportion P is finally this. Let's highlight that. So what we are doing is we take P, the unknown, and we say it's approximately equal to P hat. That's a great estimate. P hat is the statistic that estimates the population parameter P. But in order to say how reliable that is as an estimate, we add a little bit more. We take something called Z star, multiply it by the standard error, and the whole purpose of Z star is it counts the number of standard deviations that you want your statistic to be away from the population parameter P. Next, standard error is the formula that we saw above, also just duplicated here for ease of reading it out. So what we do next is calculate the critical number Z stars. And in fact, kind of nice thing about this is when it comes to confidence intervals, there's three very common levels of confidence. We did a derivation for 95% confidence, but we used the value of 2 right here because we said we want to go 2 standard deviations to the left, 2 standard deviations to the right, and that's about 95% of the area under the curve. But if we use a more accurate critical number, it wasn't really 2, it was 1.96. So Z star is the harder thing about this whole process, but that's where you're really using the central limit theorem right at this step. Yellow's probably a better color. So Z star comes from this table. That's kind of helpful. But it also means in the problem, you have to decide for what level of confidence are we estimating so we can grab the right critical number. And there's nothing really special about 90, 95, 99. You might wonder, what is Z star if you want 93.5% confidence for some reason? I mean, that's weird. That's not a round number, but there's nothing special about these numbers either. If there's some legitimate reason we want that confidence, we need to calculate Z star. But we should anyways. It helps us see what the whole process really is. Any questions, folks, before we calculate our very first Z star? Okay, so what does it do? Well, Z star is the critical value Z star, or sometimes called critical number, and it does the following. From the central limit theorem, we have this distribution. We're assuming that the sample size is large enough, the other conditions are met, so that this normal curve is an accurate model for the sampling distribution of P hat. So this is the normal curve. The center is exactly at P. So there it is, right at P. Standard deviation of this is the thing that we can't calculate. We have to estimate with the standard error, but let's throw it down anyways. It goes P times Q you could put in there, or if you put in 1 minus P, that's just as fine as a formula, and divide by N. So there's our central limit theorem. And if we are trying to go for 93.5% confidence, this number right here is doing the following. This captures, let's say it a little bit more clearly, negative Z star and positive Z star captures 0.935 of the area in the center. So we take their confidence level, turn it into a decimal, 0.935, and over here in our diagram, we'll go like this. There'll be a value to the left, value to the right, central area of 0.935. Value on the left over here is negative Z star. Value on the right is positive Z star. So our goal is just to come up with one of the numbers, one or the other. Any questions so far, folks? Okay, so kind of the cool thing about all this is it turns into a problem directly from section 5.4 using the normal model. In 5.4, we had to use this calculator to actually get our values out. And here's a good review question for the class. To get Z star, is it going to be inverse norm or normal CDF? We do have a percentage, yes. And Z star is going to be a number on the axis. Good call, absolutely. If you have the area or the percentage, it's an inverse norm process. Here's another thing that's tricky though. People's calculators are different. I think you've mentioned you have a calculator where you can put area to the left, area in the center, area in the right. So you'd probably just want to put 0.935 in the center, and it'll give you those two values. But for most calculators, we have to do this instead. We go and find this area. Inverse norm only gives area to the left. So we go 1 minus 0.935. That's not the whole story though, because if you use this, it's the complement rule. It means you're taking this area and you're finding the area on the left tail and the right tail. It's not what we want. We just want the left tail. Sorry, say again.
1 minus.
Yeah, the total area under the curve is exactly 1. So 0.935 in the middle means area on this tail and area on that tail is that quantity. But again, that's still not exactly what we want. We want only the area to the left. So we just come back over here, divide it by 2. So that's what's going to give us that area. We might as well compute it while we're at it. It is, let me just fix this window a touch. 1 minus 0.935 division by 2, and we get a 0.0325. So that's a setup so far. Should close that parenthesis there. So now finally using inverse norm, the input 1 is going to be area. It's going to be that area since we have to put in the area to the left. Next thing we're going to do is, well, this is the central limit theorem, but when we use a critical value Z star, one thing it remind us of is, let's come back over to here in the notes, all the way back to section 5.1. Z star is like Z essentially. What we're doing is we're going to subtract off the mean, divide by the standard deviation. Because of that, in this process, we're not actually using those values, and thank goodness they're unknowns in the first place. We're using this instead these values. For input 2, we set mu to 0. For input 3, we set sigma to 1. So that's the process to get our critical value. Lots of steps just to describe it, but the actual process in the calculator is super fast. It's just the portion that we wrote here in, what color is that? Plum. So finally, we're ready to give Z star. Back to the calculator. You're a little bit rusty, no worries. You hit second and the bars button close to the clear key. Pulls up all of our distributions, and we're going for option 3. Click on 3 or just scroll down and hit enter. Area is from this fraction right here. I think it's good to convey the 0.935 came from there. So from whatever confidence you're specifying, you do this formula here. So area 0.0325. The rest of the values are correct, 0 and 1. So hit enter a bunch of times, and that's our critical number. Notice what it gave us. Right, on our calculators, we have to use the left tail button.
Yeah.
Gotcha. Did you get a -1 and a positive one?
No, yeah.
Awesome. Your negative and positive should be identical, right? Awesome. So one thing that's kind of weird about our process is, notice ours is negative in our calculator, and all the values here are positive. You have to wonder, does it matter? Z star goes here, and there's already a plus and minus in front of it. It actually really doesn't even matter if you use a negative value or the positive value. You're using both signs regardless in the formula. But when you're stating a Z star, it's just more common to state the positive value. So what we did was we got the negative one. It is equal to, not that, let me try again. Negative 1.84, that's kind of hard to write sideways, 45. 1.8452 rather.
I had a different number. Maybe I did it wrong.
What value did you have right here?
For the area 0.325.
Oh, yeah, it's got to be a 0.0325. So that could have been what did it. Yep, absolutely. So next thing that happens is, even if it's negative, the positive value is 1.8452. So these values are either positive or negatives. Once you find one, you have found the other. Well, any questions about that so far, folks?
How did you get the mu and the sigma? And the, what you were saying?
Well, the idea with the critical number Z star is that Z star is much like Z. What we do here is we take our values, we're subtracting off our value mu, but in this problem, mu is P. We're dividing by the standard deviation, which is square root P, 1 minus P, divided by N. But that has the effect of, when you subtract off P, the new model is N0. When you divide by this as a standard deviation comes out as 1. So these are fixed values pretty much anytime you're going to calculate Z star.
Okay. So it's always been,
Absolutely, yes. You know, that's a good thing to mention here. Let's say it right here. These are always the values for Z star. And you know what? It's pretty fast to just check this process out again. Let's verify if that's true and just how accurate it really is. So at 95% confidence, let's redo the procedure over here. Hit second, then bars, go down to inverse norm. If it's at 95% confidence, you can just type this into your calculator. So go parenthesis 1 minus 0.95, close that parenthesis, divide by 2. We're doing the same exact thing we did here on paper. 0, 1 for those two parameter values. And we get this figure right here. Looks suspicious because it's negative, but we had that discussion. It could be positive or negative. And if you round this to, say, 2 decimal places, you're right here. Rounded to 3 decimal places, you're rounding with carry. So this is really 1.9600 if we rounded this to 4 decimal places, say. That's actually a more accurate value than it even looks like. If you wanted to, you could go like this. Just to emphasize, that's highly accurate. It's rounded to 4 decimal places from here in the calculator. But other questions or comments so far? Oh, I used a different formula. I used the value 1 minus 0.95, this one right here, which means you have to use the left tail.
okay.
Or you could have just put 95% confidence in the center. Yeah, if you go that route, just give it 95%. That'd be the easier way to go. Well, any other questions, folks, so far? Okay, so that's coming up with a critical number Z star. This is what you have to do if the confidence is weird. But the good news is that's not too very often this happens. It could happen in my lab, but I don't think any of those problems did come up that way. So think of this as a table you want to come back to often, probably something you want to put on your notes for exam 3, the final exam, because those are the more routine confidence levels. Those are the kinds of things you would expect to see on a real exam. Well, now that we have essentially everything, we can calculate critical number Z star, we can calculate a standard error, and we know how to calculate p hat. That's the whole entire confidence interval. So what we're going to do next is honest inferential statistics. Any questions or comments whatsoever? Okay, on the notes, I have 3 just kind of random problems. 2 of them we've looked at before, we checked conditions on, and now we're just doing the full procedure on. I believe this is one of them. Slightly different numbers, but here's how it goes. It begins by saying, should sound familiar, researchers in the development of new treatments for cancer patients often evaluate the effectiveness of new therapies by reporting the proportion of patients who survived for a specified period of time after completion of the treatment. So all of that's context. They didn't give us anything at all we can do with statistics. Let's just put a page break here. And now goes on to say, a new genetic treatment of 1,024 patients. Here they're giving us a sample size, N is 1024, with some particular type of cancer, who knows what it is, resulted in 173 patients surviving at least 5 years after treatment. That's the number of successes right there, surviving. So we'll say 173 successes. Let's actually highlight that just the way it is. That part of the context is really important. I mean, all of it is. But this part of the context gives us a lot. That's going to tell us what the successes are in the study. And it's going to help us do this right here. We need to describe the unknown parameter. As we should. The unknown parameter is the thing we're trying to estimate in the very, very first place. We can't say what it is. All of our formulas are basically useless. So this is, in my opinion, the hard part about statistics. The unknown parameter in this particular context is P. Not so bad because that's the only parameter we're doing inferential statistics on yet. But other times it could be mu. We have to indicate when that would happen. P is if it's categorical data. Let's actually say that here, because this will come back to get us if we're not thinking about it. P is for categorical. 2 outcomes. And we use mu. That's referred to as the population's mean, but this is going to come into play whenever we're dealing with quantitative data. So the parameter is P for categorical, mu for quantitative. We'll see this one come up later on the notes. Turns out this one's actually trickier to actually give a good confidence interval on. That's a surprise. So we'll start with P by saying P equals the population proportion of all something. Would you say it's all of what? A volunteers to fill in the ...
So, is it surviving 5 years after treatment?
Well, that would be referring to the 173 successes. So that would be describing the sample, but you're on the right track. If we said those are the successes.
So that's the population. Is it all of the patients then?
Exactly. We don't want to say all cancer patients necessarily. We want to say the ones with that type of cancer, but that's being really picky. So you say all cancer patients, I'll assume you meant that right there. But let's be specific just for the record and say the population proportion of all patients with this type of cancer that, and another ... So this always goes the same way for P and mu. Well, I'll say it a different way. This always goes the same way for P specifically, where you'll say the population proportion. This part right here is the population. And what goes here is something else. Anyone spot what it should be? Not necessarily. That would be referring to the population again.
Oh.
Exactly. We have to mention what a success is. Good call. So we'll say here, P is the population proportion of all patients with this type of cancer that, as you said, survived for 5 years after treatment. Cancer is something pretty awful. It's terrible that that's considered a real success in cancer diagnostics and treatments. But here in this portion, we mention the successes, or what a success is. Let's say it that way. That'd be a better way to verbalize this. What a success is in context. So coming up with P always goes out the same way. You're pretty much going to say something along these lines. You might say the true proportion, the population proportion, anything like that's just fine. The word all here is pretty important because it's signifying the population. Then you just say what an actual success would be in the problem. We'll practice this a lot. So if this feels kind of awful, I understand. It's one of those things where you get more practice on what we're even trying to put down on paper, the more we do it. But every statistical inference problem starts off this way because, once again, our confidence interval is for P. Next thing we do is we calculate the sample's proportion of successes. Any questions or comments first in part A? Okay, so sample proportion of successes, we need to know what that's referring to. So the moment you see this, think you're calculating P hat.
So it would be the 100, no, it would be the 1,024 patients.
Absolutely. P hat is going to be a formula that goes n in the denominator, that's the 1,024 patients. Anyone recall what should go in the numerator though?
So 173.
Absolutely. So it's always number of successes in the numerator, sample size down below. So I'll put here number of successes. Okay, got that down. Then we go in and we just fill it in. In the bottom, it's 173 successes. Or hang on, let me try this again. In the numerator, it's 173 successes. And we're dividing by sample size n, which we indicate at 1,024. So now we pretty much have P hat. Let's go 173 division 1024. Asking for 4 decimal places for precision, and we're getting 0.1689. I wanted to use a different color on that. 0.1689. Well, that's not too bad. Really, honestly, part A is kind of the hard, challenging part. And then once we get through part B, this is like the mathy portion of it. We're just grabbing the right formula, plugging in the numbers we have. And to me, this is another tricky one. When it says calculate the standard error, I'm not sure I want to use that color. Let's go with green again. When it says calculate the standard error, we say SE. If your parameter is P, we put P hat in there. But if your parameter is not P, you're using mu, we would actually say something else. Just in case you're curious, because, I mean, it is coming up. If your data is quantitative and your parameter is mu, your standard error is for Y bar, the different statistic. So back to this one, we've got standard error of P hat to match with the parameter P. Formula goes square root of P hat. Author puts Q hat next, but I'm kind of feeling like this is a better way to go because it's just telling you right away, that's what goes in no matter what. That is your Q hat. Divide the whole thing by sample size n. We might have done this yesterday, but let's do it again. It's not too fast. It's good practice. Or excuse me, it's not, doesn't take too long. So in place of P hat, just go to part B and throw in 0.1689. Then 1 minus the same value, 0.1689. Finally, division by sample size, 1,024. And we just need to shove that stuff into the calculator. So we've practiced this a lot, you might have noticed, but that's because a lot of times when we go to do this procedure, this is where the simplest mistake in a calculator will happen. Oftentimes people have it perfect on paper, but it's easy to just miskey something. So let's go second power 2 button for the root, 0.1689. 1 minus 0.1689. They hit division 1024. So that's one way to do it. We get a result of 0.0117. That's to 4 decimal places, 0.0117. Still, you're able to rescue that. You can just take square root of your last answer. 0.0117. That's a way to calculate it. We've shown how to do this a number of different ways. But if you're the kind of person who always wants to be as precise as humanly possible, here's another way to go. You don't have to do it this way. This is, again, for people who want the most possibly accurate answer you can ever get. Go like this in your calculator. Put in p hat as 173. Divide by 1,024. The calculator displays this number, but it's really storing that number right here when we call up that computation. So next, we're going to throw in square root, second power 2 button, and instead of typing in just 4 numbers, up arrow. Hit enter there, and that's as accurate as possible. In fact, this has not been rounded. It's thinking in the calculator this figure actually, totally accurate. Then parenthesis, 1 minus, same trick. Up arrow, hit enter. If that doesn't work on your calculator, you might have a slightly older one. You can also do this. Second, and the negative sign calls in your prior answer, which is referring to this. Close a parenthesis, no rounding has occurred here. Divide by 1024. Then the only rounding that occurs is when it displays the output. We get 0.0117. Well, we're still just as accurate to 4 decimal places, but this is now a more accurate figure if you want, say, 6 decimal places of accuracy. And honestly, it's kind of a fast way to put it in. So it's good to have options, and either way, we've got a standard error. Any questions at all, folks, coming up with that number? Okay, continuing on. It's asking, are the conditions for the large sample confidence interval met? And this is kind of a tricky question in a certain sense. You might be thinking all of these conditions, the assumptions and conditions. But really, if we're doing a direct confidence interval computation, when it asks for conditions, we're just thinking these two right here. So to estimate P, it says we must first check the following conditions. Let's grab them for easy reference and do just that. So first thing we need to determine is the sample random? I have no idea. Let's take a look. It says here, eugenic patients of a particular type of cancer. It just says of 1,024 patients. No information whatsoever on this being a random sample. So we'll come down here and say, it's unknown. If this was a random sample. That's a bit problematic. And if you read these kind of medical journals in the sciences, a lot of times the samples really aren't random, and they make some wild types of arguments saying, but for this kind of cancer, our sample is representative of the population of all cancer patients. That could be a true statement, but it's something that we should be a little bit skeptical of. That's why sometimes these articles are really, really thick, because they have to say a lot to justify that kind of information. Best thing to do is try to get a random sample if you can get one. This one, we don't even know if it was random or not. But the next thing we can check is the sample size large enough? You could use this formula, but keep in mind if you just have a count of your successes and failures, it might be just as easy to list them out. So back to the top of our problem, we had 173 successes, so we can now say number of successes equals 173. Seems silly to say greater than or equal to 10, but this is just a reminder we crossed that benchmark very, very nicely. Then number of failures, we calculate this way. We take the total sample size, n, 1024. There are only successes and failures. There's no intermediate outcome. So subtract off the successes and you have all the failures. Minus 173. I think I want to go down the line on that actually. So 1024 minus 173. There's no way I'm going to try to do that in my head.
851.
Sorry, say again.
851.
Awesome, thank you. 851 definitely meets that benchmark. Both of these are greater than or equal to 10. And so we can say this is the confidence inspiring part. The sample size is large enough. Let's highlight in yellow just to say it's large enough because greater than or equal to 10. So for the larger question of are the conditions for the sample met? We don't know because we don't know if it was really a random sample. All we know is that the sample was large enough for accuracy. And so if you like, you can give an overall conclusion that would say the conditions are met so long as the sample is random. And that's a weird statement again, because they didn't tell us it was random, but we can't immediately assume it was not. It's just up in the air now. So this is kind of like a disclaimer statement. Our conclusion will be accurate as long as it really was a random sample, but we can't ascertain that at the moment, is what we're trying to say. Well, we've covered our tail with that statement there, but any other questions with the conditions? Oh, this is what if you had a problem that looked like, say, this one over here. I think we had a p-hat come up just once. It would have been in section 13.2. I think it's the very last problem. We were checking not the conditions of the confidence interval. We were checking all of the assumptions and conditions for the central limit theorem. And in one of those problems, let's see, this one, it didn't even tell us the number of successes or failures. They just told us p-hat is 0.2035. So when we went to calculate successes and failures, in that one context, we really had to use that formula here.
So we don't have anything.
Exactly. That's a great way to say it. So you have just p-hat, we do this. But in our other problem we were looking at, it was more like this one right here, where they told us the successes was 25. So we just dropped that there. Hang on, where is that? No, that is not true. The number of successes was 8. The sample size is 25. So we just stated there's only 8 successes and we said conditions were not met. That's similar to what we did on this problem here. But other questions about that so far? Okay, thanks for asking about that. I honestly feel like this is one of the other really tricky portions because problems like this one are pretty common where they tell you the number of successes, but in that one time where they don't and they give you a p-hat instead, that's a really confusing situation. So that's the one and only time you really need to use these formulas down right here. Well, we have our conditions checked. We don't know the exact outcome due to randomization being up in the air. But in this case, we can start stitching everything together and calculate the confidence interval. So that's our part E. Let's give it plenty of space. It's only our first time doing it. To get the confidence interval, we need a few things. First thing we should do is just write down the formula. I think that's sensible. It is p-hat, add or subtract a critical number, z star, we'll find that number, and multiply by the standard error of p-hat. So really first thing we have to do is come up with z star. Getting z star involves the level of confidence. So here's what we can say. C equals 0.95 means Z star equals, and you might have memorized this, but if you haven't, just go up to this part of the notes. That table is fantastic. Gives you pretty much everything you would want on a normal problem. And at 95% confidence, we have this value. But let's screenshot this and put it in the problem just to emphasize this is where we got it. So let's dump this. That's way too far. Here. So to get our Z star, we grab the 95% confidence and put in 1.96. I kind of like 1.9600 because it reminds us that's an impressive amount of accuracy as opposed to the other ones. But finally, with all these things in play, let's highlight yellow just to show where things are going. We can just start dropping in information. Starting with p hat. Guess we have to look up a lot of things here. Sorry for the scrolling. Let's just take all of this so we're not doing it too much. I feel like you could get seasick from scrolling up and down all class time. So next thing we're putting in, right here, just dump in p hat, 1.689. If you give the fraction, that's okay too, but I think most people would go this route. 0.1689. And subtract the critical number. That's the 1.96 coming from here. Multiply it by the standard error of p hat. Remember, this is all one symbol. It's not saying something multiplied by p hat. So we only give that one number, 0.0117. And that's our entire confidence interval. It takes a long time just to get there, and it's almost strange how fast it is to fill in once we have all the right information. So I guess we're done with that screenshot. Now all we're going to do is perform the computation. Any questions at the moment? Okay, so the plus right here.
Yeah.
Well, it has to be a plus and a minus at the same time. Yeah, absolutely. The reason for that is what we're going to say is p hat is at the center of the interval, but the minus is the distance we have to go to the left, and the plus is the distance we have to go to the right. To be 95% confidence, the parameter is actually in our interval. So we're going in two directions on this thing. P hat is just the center of the interval. Other questions so far? Okay, let's type this into the calculator. It is tedious, but this is why we've been emphasizing shortcuts all of the time. This is a great shortcut to use right here. Type it in once really carefully. 0.1689, throw in a minus, 1.96, parenthesis 0.0117. Close that parenthesis and hit enter, and you have the lower bound of the confidence interval. We're rounding this to 3 decimal places, so it's a 0.146. I'm going to put a less than because there's a really important thought we have to put here. This is a confidence interval for the unknown parameter. The unknown parameter is what we specified in part A. It's P, true proportions of patients that will survive after 5 years when they have that cancer in the new treatment. So that's what we're really estimating in the middle. It'll be less than, we do the computation again, but now we're using plus. So that means in your calculator, up arrow, hit enter to highlight it and pull it down, and just move all the way to the left here so that you're in this position and the right it. Overwrite it with a plus. And that doesn't seem huge, but typing this in is tedious. And if you do it twice, in my opinion, that's more than double the chance of making a mistake because it's frustrating to type it in twice. It just feels like busy work. That could save you a lot of time in my stats lab, especially when it's easy to key in a number incorrectly. To 3 decimal places, that's 1.92. Excuse me, 0.192. Right, yeah, I had to do a double take in my mind as well. 0.192. Well, we've got it, folks. That is our confidence interval for the unknown parameter P. Any questions at all getting to this stage of the work? Okay, well, let me just try to get these. That should be just fine to hear. Next thing we have to do once we calculate the confidence interval is when we look at that, we have to be able to say what it even means, right? Because everything we do in statistics is of zero value, literally zero value, unless we can explain its meaning. And with statistics, the audience we're explaining it to are not statisticians. We're not explaining what this is to an audience of fellow students in a statistics class either. We're trying to explain what that is to someone who has never taken statistics in their life. Imagine you're maybe, say, a reporter trying to disseminate information to the public. You have to tell the public exactly what that means. So in doing that, here's what we do next. This part is the reason why we emphasize the context massively every step of the way in statistics, because we come back up here, grab all of this, that's our context. So whatever you say in part A, just pull it down to your conclusion. And even if you made a mistake in part A, no worries, you'll still get full credit. So here's how it goes. We'll write it out carefully, mentioning each part that we have to state. So give a practical interpretation of the confidence interval. They're referring to this up here using the context. So one thing you can never do is just mention the interval without saying how confident you are. That's extremely important because without saying the level of confidence, we have lied massively with statistics. And here's one reason why. Notice as your confidence goes down, Z star is smaller. That's kind of interesting, right? If you want to be more confident, your interval should be wider. Widening out your interval means a larger number in Z star. So if you're 99% confident, that's great. You have high confidence in your output, but Z star is huge and your interval is much more wider. People like narrow intervals because it sounds like they're being more precise. So someone could do this with statistics. Imagine we're calculating Z star again. Hit second, vars, inverse norm, and instead of 95% confidence, suppose we drop the confidence to 10%. I mean, why not? You can still get Z star. You can get Z star for any value of confidence between 0 and 100%. If you did that, Z star is now 0.125 instead of a 1.6. It's extremely small. If you plug that here, your interval is now extremely narrow. And it looks like, well done, everybody. We did a really great job estimating. But no, we didn't. Our confidence is dropped down to the floor. So the most important thing we have to do in our interpretation is say the following. With 95% confidence, here we're stating the accuracy in our confidence for the interval to really capture P. This is the probability that the method works, essentially. So we state that right out of the gate. With 95% confidence, here's the tedious part. We need to read out our parameter because that's what's in the middle. And if we're interpreting it, we have to mention it. So with 95% confidence, the true proportion of all patients that have this cancer and survive for 5 years after treatment is between, we do need to say between because we have a lower bound of an estimate and an upper bound of an estimate. And this is kind of the choose your own adventure part. In a quiz or an exam problem, I don't care if you give me the proportion or if you give me a percentage, totally up to you. In my stats lab, watch out for the boxes where you put these in. If there's a percent symbol next to it, you have to convert it to a percentage. But in my opinion, for a nice practical interpretation, most people would understand percentages is always better. So I'll write this as 14.6% and 19.2%. Those are really bleak numbers, but we can imagine maybe the cancer itself is extremely vicious, metastasizes right away. So this could be a really good outcome for bad cancer. Yeah, it would be normally. So we can imagine maybe the cancer is just horrific and almost everybody dies. And maybe this is a breakthrough actually. Without more context, it looks pretty bad though. But any questions at all, folks, getting to that last portion? Okay, so essentially, this is the confidence interval, but what we put in the middle is a parameter p. And we go to write this out, that's what we're trying to express. So just to make a couple of comments, should have thought of that and put an extra space up here. Let's reiterate some of the things we said. We must state confidence level. And then the other thing is, we must restate, I know this is kind of tedious, restate what P represents. It's kind of tedious to write it out 2 different times, but I've been teaching statistics for a really long time, and I found if you write it out once at the very start, your subconscious is chewing on it the whole entire time. And by putting in this part A, it just makes everyone's exams grades actually go up. It seems like that's just the best way to approach the problem. So I'll always put this as the first part on a real exam or quiz problem, but then we do have to write out one additional time in our overall conclusion. Sorry about the tedious part right there. Well, any questions at all, folks, with our overall conclusion? Okay, so we have a confidence interval from 0.146 to 1.92. Let's just mention a couple remarks about what we've got so far. The interval can also be written this way. The interval is, if you like writing out mathematical intervals, it'd be an open parenthesis 0.146, comma, 0.192. So our interval is always that. But another thing that's interesting about this interval is what is in the center. It's kind of weird. I wrote that as a question. Let's take a look. You can find out what's in the center by taking the upper bound of the interval, 0.192, then subtract, 0.192 and then add, had a brain fart there, add 0.146, divided by 2, and that's the center of our interval, 0.169. But that should feel familiar, 0.169, that's just this value, p hat. So our interval is rounded, that's why we're not getting all 4 decimal places of accuracy, but that is p hat at the dead center. You should get a 0.338.
Well, I just did divide by 2.
Yeah. And you should.
I got 0.5.
Very strange. Try doing it this way, 0.338, then just division by 2 like this, just to see what the calculator does. It should be a 0.169.
That way.
Oh, I think what could be going on is, are you putting it in one line?
Yeah.
Oh, you might need parentheses around your numerator then, is what it would be. So in one line, it's 0.146 plus 0.192, close parenthesis, division by 2 to get it that way.
Yeah, okay.
Awesome. So the punchline is p hat is the exact center. Deserves an exclamation mark there. It should be the center, because if we go back all the way to the very start of the class, we've done this a couple times, we'll stop doing this after a certain point. P hat is our best estimate of P itself, the unknown parameter. So it better be in the very center of that confidence interval, or else something is a little bit just off. We also said, in order for this to be a decent estimate, we must describe how reliable the estimate is. In other words, we need to say what the error is in making that estimation, but we kind of have the moment we write out the interval. Let's pull down this part right here. So when we look at this, the margin of error in estimating P, that's the unknown, approximated by P hat, the known statistic, is this portion. Just trying to figure out which arrows. Let me see the best way to draw an arrow to express this. So it is this portion right here. Margin of error. So the 1.869, that's the P hat, which is approximately P. And this number is the distance you have to go to the left, the distance you have to go to the right, so that the total interval from here to here has a 95% chance of capturing the unknown parameter. So that's our margin of error right here. Well, any other questions, folks, so far? Okay, as a formula, although we won't use it too often in this class, if you're curious, it's written this way as well. M equals Z star times standard error of P hat. This is another way to express the margin of error. So there's lots of things we can say about these kinds of confidence intervals, but that's what we're going to start looking into step by step. On our next problem, we'll do another full analysis, ending with the conclusion, and then we'll have concept questions down at the very end to just go a little bit further in this direction. There's not a ton of concept questions I'm going to ask on a real exam. Think of these problems that we just solved right here. The next ones, all these examples, these are pretty much the real exam problems. I might take out a couple parts just to make it a little bit shorter, like checking the conditions, for example. We might make that its own problem. But these are the routine exam problems you'll see. Anything that's more of a concept question is more to help out in the MyStats lab. Well, let's see where we're at. We've got about 12 minutes and some change, and a whole nother problem. Any questions first before we take another look at this one?
Do you give us the main difference between Z score and Z star?
Oh, yeah, absolutely. Let's put it maybe right over here. So Z itself as a Z score, which is equal to Z, or let's write it this way. A Z score is Z equals Y minus, we can either put Y bar or mu. Let's put it the way that's written originally, divide by S, and this counts the number of standard deviations that Y is away from Y bar. Now let's highlight a couple things. Y bar is blue to remind us that's going to take the role of the parameter essentially. Y is green. This highlighting just looks kind of funny. Let me write it this way. Okay, so that's our setup so far. Now we go to Z star, the interesting one. Z star is the critical number, or you could call it the critical value, anything like that. Z star is the critical number that counts the number of standard deviations that in place of Y, we put P hat is away from. And in place of y bar, we put the parameter p itself. So z-star is counting standard deviations in the same exact way the z-score itself is. Kind of nice to see that sort of parallelism. It's satisfying in a way. But does that make sense on the difference between the two? Awesome. Well, are there any other questions at the moment? Okay. Well, let's take a look at this next problem right here. We're not going to get too far into this analysis, but let's just see if we can get down the parameter and go from there. We looked at this problem earlier, so it's kind of a rehash. I do have a third example that's totally new, so there'll be more variety. To evaluate the routine policy of vaccinations of infants for whooping cough, we're told adverse reactions were monitored in 339 infants. That gave us a sample size. And it's really important to write this down immediately because that's going in a formula. The moment you start thinking about it, writing it down, your subconscious is already working with it. Makes the formulas much easier to approach. So 339, it says reactions were noted in 20.35% of the infants. So 20.35% of the sample represents the successes, having an adverse reaction. That gave us p-hat. 0.2035. We have to put it in as a decimal form for computation. And here is once again the trickiest part of this whole thing. We want to describe the unknown parameter p. We'll start by saying p equals, you can say true proportion, population proportion. It's a stylistic choice, all up to you. Let's go with true proportion again. Of all, and all of what? Is it all vaccines, all infants? What would you say to this part?
All infants.
Absolutely. True proportion of all infants. We don't know if this was all infants on the entire planet, all infants in a particular nation, a particular county, locale. We're not too sure.
What all infants you got? You still working on?
Well, they only monitored 339,
Oh.
and they want to give this vaccine to all infants, whether they have the whooping cough or not.
Okay, that makes sense.
Awesome. Other questions at the moment? Okay, so we've got our population right here. True proportion of all infants that have. From here, we are mentioning the success. Should we say all infants that have no reaction or all infants that have a reaction? Good call. This right here is indicating the success. So yes, absolutely. It'll be all infants that have or had a reaction. Let's say an adverse. We don't know how serious or mild, but it was an adverse reaction to the vaccine. So we did it, folks. That's our parameter readout on this one. When we said all infants, that was the population. And when we said have an adverse reaction to the vaccine, this was a success in this context. So that's our parameter. We're going to try to squish between two different numbers, forming out the confidence interval. But I don't think we're going to be able to get through it, even if we try to rush through it. I mean, that'd be not kind of fair to try to figure that out. So we'll come back on Monday's class and work through this one. But any last questions, folks, on what's going on with these confidence intervals? Okay, well, have a great weekend, folks. Have a safe Halloween, and we'll reconvene right back here on Monday. We're getting pretty far through the course, so we're hitting all the major things we want to get to.